So let's talk about more bonding. Only we're gonna progress through actually chronological order as these theories developed, and honed in a little closer on actually what's happening in the bond itself. We talked about, we've made Lewis structures. We've talked about ionic bonding, that we brushed that off pretty quick. And then we get into covalent bonding. And our Lewis structures allow us, with the aid of the VSEPR model, to predict their geometry. And the geometry of methane should be, if we draw it like that, one, count valence electrons, 1, 2, 3, 4, plus 4 is 8, 2, 4, 6, 8. So we used them all up. Now the VSEPR says that we have 4 groups around that central atom. We ought to have a tetrahedron as our electronic structure, and in this case, our molecular structure as well. So, and that's true. The physical evidence, laboratory experiments confirm this shape for that molecule. All the bonds are exactly equal. They're positioned as far apart from each other as possible, which is the tetrahedron. But that's a practical application that we cannot explain with the valence bond theory. And the valence bond theory says those valence electrons belong to carbon and hydrogen, 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 hydrogen. And the bonding comes from the overlap of orbitals, of those atomic orbitals. Okay? So here's the problem. This tetrahedron, and the bond angles, of course, are 109.5. Right? That's all confirmed. But we cannot explain it with atomic orbitals. And here's why. This is the valence shell, 2s2p2. Well, actually, if I write it the way we've done it before, 2p2, and actually the core, of course, you have those two, 2, 4, 6 for carbon. Right? Yeah, carbon. So here's the valence shell, and we've got 4 electrons in here that can share with 4 electrons from these hydrogens, so we're good there. The problem is the geometry is not right. These 2 orbitals are spherical, right? So the overlap could occur anywhere. These p orbitals are dumbbells, and they point off in 3 different directions corresponding to x, y, and z axes. Right? So if you overlap these 2 with 2 hydrogens and these 2 with the other 2 hydrogens, you do not get a symmetrical molecule. So that's one of the places that the valence bond theory and the models that come from it fail. Okay, so here's the answer. We tweak. Okay, and here's the tweak. It's called hybridization. We hybridize orbitals. In fact, we mix these s and p orbitals. And remember, p has x, y, and z available, and s only has 1. So if we mix this one s and those 3 p's together, we get 4 equivalent orbitals, because we have to come out with the same we put in. That's just logic. So if we're going with 1 here and 3 there, we come out with 4 equivalent orbitals. Now we identify those orbitals as sp3. That just means we use 1 s and 3 p's to make this hybrid orbital. And now we have 4 equivalent hybrid orbitals that are spaced as far apart from each other as possible, which means tetrahedron. All right. Actually, this fix to the theory was proposed by Linus Pauling, and that seems logical to me. I mean, he's the one who pulled it all together and made sense of the bond, the chemical bond up to that point, and got him a Nobel Prize for it. Back when Nobel Prizes meant something, you know, now they're worthless. Except for a few rare occasions, maybe in medicine and maybe even in physics still. But the rest of them are pretty much worthless. Okay, so this theory hybridizes those atomic orbitals, and these hybrid orbitals are still considered atomic orbitals. They belong to carbon, right? They don't belong to the whole molecule, just to carbon. Now, obviously, these orbitals don't form in free carbon. Like one carbon atom would not have any of these orbitals right here. It doesn't need them. It has the original structure. But once we enter into this association with 4 other hydrogens, these hybrid orbitals develop to accommodate them. So the bonding itself is what stimulates the production of these hybrid orbitals. And of course, you got to remember, nature just does what it does. This is our explanation for it. Okay. Let's see. Of course, the individual atom before the bonding is described by quantum mechanical models, wave functions. Right? We're not going to go into those details. Just to say that when we create this hybrid, the wave functions, the mathematical models must be modified to accommodate. And we're talking about probabilities. You know, where are the electrons located? Probably, most likely. What are their energy levels? And all of that's contained in the model that must accommodate this hybridization. So it's more than just doing this little tweak here. I mean, it goes deep, mathematical, probably with the aid of some powerful computers. Okay, so this hybridization, in fact, this Sp3 hybridization is always associated with the tetrahedron electronic geometry. And the reason I say it's associated with the electronic geometry is because you use the same hybridization for ammonia, right? Ammonia has an electronic tetrahedron because it has these 2 lone pairs, and then it has a hydrogen here and a hydrogen here and one in the back. That's what makes that like that. So, and there are slides to back this up. Those lone pairs go into one of those Sp3 hybrids. So we use the association of Sp3 hybridization with the tetrahedron electronic geometry. The same thing would work for water, which has a tetrahedral electronic geometry. But since it's got 2 lone pairs, it's a bent molecule. It's a bent molecule. Okay. So this slide tells us a little bit about what we expect from the energies of these hybrid orbitals. Now, it doesn't tell us the values right here. What would that value be? Don't know. The model doesn't tell us. But it does tell us that the energy of these orbitals should be somewhere between the P's and S's. So 2s mixes together with these 3 P's. And since there are 3 of them at this high level, you're going to find this somewhat closer to the P's than the S's. So those 4 equivalent orbitals, they're called degenerate orbitals. That doesn't mean they're morally depraved. In chemical terms, that means they are equal in energy. Okay, so this is the mathematical, the computer would spit out this electronic density model to show where the electrons are likely to be found. This is sort of a shape. Whereas these would be dumbbells, right? And this would be spherical. These 4 equivalent orbitals would be pointed toward the corners of the tetrahedron. So that's why they're kind of offset in between the axes like this. Okay, and that's what our molecule would look like. And you're still overlapping atomic orbitals. Carbon's Sp3 hybrid orbitals overlap with the 1s orbitals on each of these hydrogens to give you the tetrahedron. Okay. Oh, okay. I sort of jumped the gun with ammonia. Here's a more complete description of the ammonia. And you do the same thing that we've always done. You don't invoke hybridization until the very end. So you draw the Lewis structure. You say, all right, what's the structure supposed to be using the VSEPR model? Then you determine the hybridization that's required from the electronic geometry in that order. So ammonia would do this, right? You have 3 hydrogens and 1 lone pair. We've done that before, drawn the Lewis structure. So you have 4 groups around the central atom. That means it's tetrahedral. That means it has to be an Sp3 hybrid. The 2s and the 2p's hybridize together from nitrogen. Hydrogen doesn't have to hybridize, doesn't need to. Sometimes, if this is paired with, say, another nitrogen, then that other nitrogen might have to hybridize also. So we're still talking about the central atom. Even there might be several central atoms in the group, in the whole molecule. Okay, so it uses 3 of those Sp3s for actual bonding with the hydrogens, and the 4th one is occupied by the lone pair of electrons. Now, of course, the bond angle we predict for a tetrahedron is 109.5 degrees. But with that lone pair up there, remember, lone pairs that are not in a bond tend to balloon. So their charge spreads out some and compresses the others. So the actual bond angle is less than 109.5. Okay, how about ethylene? So what's ethylene? We can draw the Lewis structure for ethylene. Right? 2 carbons are bound together, and then the 4 hydrogens are attached to each one of these. The reason I'm drawing it out like this is to illustrate the conventions that are associated with organic chemistry. When you see written like this, those 2 carbons are bound together, and then the hydrogens are bound to the carbons like this in a balanced fashion. So we have, let's see, 4, 8, and 4 is 12. 12 electrons, 2, 4, 6, 8, 10. So it means we have 2 electrons left over. Hydrogens can't take anymore. So we just put them on one of these carbons, and then we try to make the octet, right? So each carbon has only 6. If we take that pair and make another bond here, now we've used up all our electrons, and everybody's got an octet. Okay? So around each of these carbons, they appear to be equivalent. 1, 2, 3, 1, 2, 3 groups around each one. So if we describe one, we describe the other. What do 3 groups mean? Trigonal Planar. Okay? Now we only need 3 equivalent bonds with 120-degree angles. Right? So if we're going to hybridize this one, you start with the lowest energy, S, and then how many P's do you need to make 3? Just 2 more, right? So we only need 2 P's to make the hybrid orbital for this carbon, Sp2 hybridization. Okay? But what does that do? Well, if an X and a Y went into this one, then you got this Z sitting out here all by itself, unused. Okay? Well, unused until I tell you what happens to it. right? So the trigonal planar requires Sp2. And the bond angles have to be 120 degrees. And that is, in fact, what we see here. So Sp3 can't account for it because we don't have 4 equivalent orbitals. We only have 3. So Sp2 is required to hybridize. And now we've got, let's draw it this way, temporarily. We've hybridized Sp2s to give us these equivalent orbitals. Now we've got these unused P's right here. So guess what happened to those? They overlap, and that gives us that double bond. Now this doesn't give us 2 bonds because this still is a single orbital. So the overlap, in fact, is not. It's kind of like a pillow on top and a pillow on the bottom. Those are just probabilities for finding the electrons in that region. And there's still only 2 electrons in here, even though it looks like we've got 2 separate bonds. We don't. We've got 1 bond here, and we're going to name it later. I might as well name it now. If you have a bond between 2 atoms on axis, that's called a sigma bond. Okay? You always have at least one of those if there's a bond. Then if you need off-axis bonding, like this one, that one's called a pi bond. That'll come later. We'll talk about it a little more later. But I figure stream of consciousness, this is a good place to introduce it. You can also have another pi bond over here. Like if this were acetylene, like that, you'd have 2 pi bonds and a triple bond for acetylene. This is ethylene, that's acetylene. Or sometimes you'll see it written ethene. No, ethine, excuse me, ethine. Okay, I won't spend too much time on that right now. Oh, there it is. Snuck up on me. So that's what we mean by sigma bond versus pi bond. You always have at least 1 sigma bond and only 1 sigma bond between 2 atoms because it's on axis, there's only room for 1 bond. But off axis, you could have a bond forming in this plane, or if you have an unused coming in and out of the board, you can still overlap those, and that would make your other pi bond. Because the p orbitals are x, y, and z. Right? We've already used the one on the x-axis to hybridize and make the rest of them, make the hybrid orbitals. So now, in this case, we really only have 1. So I'm making a mess up here. Okay, so this is what the energy looks like. Again, the hybridized orbital is somewhere between the S and the P in this case. And this unused is still at the same level. So in this case, we only have 3 degenerate orbitals. And we have 1 original. And that's the one that creates the double bond. This is an artist's idea of what it would look like. Okay. And here's another computer-generated model. Okay, so now we get this overlap of these orbitals, these p orbitals, and that's where your double bond comes from, your pi bond. All right. How about CO2? Carbon dioxide. Got carbon, carbon and an oxygen and an oxygen. Okay, so that's 2, 4. But we have 6, 12, 16. So we have 12 electrons left over. All used up. Okay. So now we want to make an octet. The best way to make an octet out of these is to move that pair over here, make another bond. That still preserves oxygen's octet and works into carbon's octet. We could make a triple bond on that side and a single bond on this side. But how do we know that's not the best one? Remember formal charges. You calculate the formal charge, you find that it's way out of balance. If we make the double bond from this side, then we're balanced. And in fact, the formal charge of each one of these is 0. Right? 6 minus 1, 2, 3, 4, 5, 6. 0 there. 4 minus 1, 2, 3, 4. They're all, that's the best model. Okay, so now the VSEPR says we have a linear structure. Right? 2 groups means linear. So that means we only need 2 hybrid orbitals. So we start with S. Now we only need to use 1 P. So the hybridization on carbon in this case is Sp. So what's left over? What's left over is 1 that way and then 1 out of the board like that. 2 unused P orbitals. So we've got a PX and a PY. PY and PZ. Let me be consistent. The X went into this hybridization. Well, how are we going to overlap with oxygen? Well, look at oxygen. It's got 1, 2, 3. It's got 3 electron groups around it, which means trigonal planar, right? So its hybridization is Sp2. Sp2 for oxygen. 1, 2, 3. Remember, we're still talking about electronic structure. So 1, 2, 3 groups means Sp2 hybridization, but it has an unused like that, and then this one would have to come like this in order to make sense out of it. This one overlaps with that one there, and this one overlaps with this one. So that's where this pi bond comes from, and that pi bond comes from. P orbital overlap. Okay. Bond angles, of course, are 180 degrees. And Sp hybridization explains, with our tweak, how that happens using atomic orbitals only. In this case, hybridized atomic orbitals. Okay, so here we have 2 degenerate Sp orbitals. Yeah, 2 degenerate Sp orbitals and 2 degenerate unused P orbitals. This is for carbon only. We're not talking about oxygen yet. That's what it would look like, how they're positioned, so we get this linear molecule. And this is an illustration of the overlap. So these overlap here, and then these overlap there. That's another way to look at it. This also illustrates the Sp2 hybridization for the oxygens. And this only forms the Sp2 from oxygen and Sp from carbon overlap and make the sigma bond in between. The previous slide shows us the pi bonds. I probably should switch them. Do the sigma bonds first and then the pi's. So how about the N2 molecule? Okay. Well, around each nitrogen is 2 groups. 1, 2, 1, 2. Okay. So it's hybridized to Sp. Linear, right? Only 2 groups means linear electronic structure for that nitrogen, and this is a mirror image, it's the same thing. Both of them are Sp hybridized. So that leaves 2 unused P orbitals on both of them. One from one from the other overlap, make a pi bond. And the other ones overlap, make another pi bond. So we get a sigma and 2 pi's to make that triple bond. Okay. Let's see, is it going to show us? Yeah, it's going to show us a model. So here we have our hybrid orbitals, and there are unused P's, and the P's overlap and the hybrid orbitals give us the sigma bonds. Okay. The lone pair occupies an sp orbital on each nitrogen atom. That's right. You've got two sps. So one sp overlaps with the other sp for the nitrogen makes a sigma. But the lone pairs occupy these positions. Okay, how about PCl5? PCl5. We need to, phosphorus is 5 and 7 each here, so that's 35 and 5 is 40 electrons, valence electrons. So phosphorus, and then we have 1, 2, 3, 4, 5 chlorines. Okay, 2, 4, 6, 2, 4, 6, 8, 10. Needs 30 left over. 6 more around each chlorine means 30. So that uses them all up. If we put these electrons, okay, what's the and they're all used up, and P exceeds the octet, right? Now, we described and explained how phosphorus can do that. How can it exceed the octet? Well, phosphorus is in the third period. Right? When n equals 3, you have access to S, P, and D. So D gets involved here. Right? Now we're going to show you how it gets involved using hybridization. Right? What's the structure here? It's a trigonal bipyramid, which means 5. We need 5 hybridized orbitals to give us that structure. It's going to be like this, 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 and then there and there. Phosphorus in the middle, and chlorines all around. Okay, so if you need 5, we're all out of S's and P's, right? Sp3 is a tetrahedron, that doesn't work. So we need to dip into a D. So we pull out a D, and instead of putting it on the end where it logically should be, because we're going from low to high energy, I guess there's some aesthetics involved. Instead, we call it DSP3. That gives us 5 equivalent hybridized orbitals to make that molecule. Oh, and bond angles, right? You can have 180 here. You can have 120 around the triangle, but between this chlorine and that chlorine is the 90 degree. So this one's a little problematic. Earlier with the trigonal planar and the tetrahedral, those hybridized orbitals were all equivalent and spaced properly. So now we have to sort of stretch your imagination and say, okay, they may be equivalent in energy, but the geometry is a little off. We just accept it because this is a tweak after all. May not be reality. It's only good as far as it explains things. So DSP3 hybridization gives you 5 equivalent orbitals, and I say degenerate orbitals because they're all the same energy level. Okay, how about this one? Xenon tetrafluoride. And we got xenon, and we got 4 fluorines, correct? Okay, xenon is 8. 7 times 4 is 28. So we've got 36 electrons. 2, 4, 6, 8. That's 28. Right, if we put 6 around each fluorine, then 4 times 6 is 24. That leaves us with 4 unused electrons. Fluorine's full. We got to put them here around the xenon. No problem. See where xenon is? In the 5th period. It's got oodles of extra orbitals that can use. So how many groups do we have? 1, 2, 3, 4, 5, 6. So the electronic structure is going to be octahedral. Right? Like a square here. And then your xenons in the middle, and you have one up here and one down here. So with octahedrals, if you have lone pairs, the lone pairs for an octahedral tend to go on the apices, like here and here. Remember the trigonal bipyramids, they like to go on the triangle for some strange reason. And then the fluorines are positioned like this. That's a square planar molecule, but an octahedral electronic configuration. So we need 4, 5, 6. We need 6 degenerate orbitals to work this magic. So we pull out another D, D2Sp. So that's the hybridization for this one. And notice the number of groups for your electrons, 6, 3, 4, 5, 6. Right? You just start with your S's and hybridize an Sp if you only need 2 groups. Sp2 if you need 3, Sp3 if you need 4, Dsp3 if you need 5, and D2Sp3 if you need 6. And that's as far as we'll go. Yeah.
I want to ask, how do you find how many groups you use again?
Oh, it's best to look at the Lewis dot structure. 1, 2, 3, 4, 5, 6.
Okay.
Once you start putting them in this geometry, then it's a little harder to follow. Unless you're lost already. I see wonderment back there. Actually, it's confusion.
Yeah. So we're just like, we drew the dot structure.
Right.
Now we're going further into the structure with the orbitals and stuff like that.
Right. We're trying to explain why the VSEPR works.
Okay.
Yeah. And that's what the hybridization tweak is all about.
Okay.
Okay. So we have octahedral electronic structure. This says 90 and 180 degrees. That's true if you have enough atoms bonded to the xenon to put a couple at the apices. But in this case, all we have is lone pairs of electrons. So really, we don't have 180 degrees here. We only have 90 because all the fluorines are on that square at 90-degree angles. Okay, D2Sp3 hybridization takes care of that. And we also know that we don't have Sp3 hybridization, not just because we have 6 groups to deal with, but because the physical evidence says that the structure of the molecule is square planar. And square planar does not satisfy Sp3. Sp3 is tetrahedral only. So square planar only works if you have octahedral with 2 lone pairs. Okay. So this is what it looks like. Fluorine doesn't have to hybridize. All it needs is that outermost, let's see, 2p orbital. The valence 2p, and it'll overlap with the hybridized orbital from xenon. Okay. Let's see. I want to be sure and cover everything, but I want to be, I've got to quit on time. I think I can make it. And since we're not going to be meeting until after the holidays for part 2, if you're ambitious, there are older videos that cover everything that we can get to today. So if you have some spare time on the holidays, and you're just itching to do some chemistry, the videos are there.
Well, I got a 4-hour flight, so I might watch it.
There you go. That's the ticket. Okay, so hydrogen cyanide, we've done this one before, the Lewis dot structure. Like that. Which means around this central atom, you've got two groups, which is linear, right? So it has to be Sp hybridized. Around this one, you've got 1, 2 groups, which is linear also. And it's Sp hybridized. So one Sp orbital makes a sigma this way. Both of the Sps make a sigma that way and a sigma this way on carbon. And the other Sp orbital is occupied by a lone pair. Okay. Now the triple bond, we have a sigma in the middle, it's already accounted for. This pi bond is overlap of unused p orbitals. And then we have into and out of the plane of the board overlapping to make the other pi bond. Okay. There we go. That's a sigma bond. That's a sigma bond. That's a pi bond, and that's a pi bond. Okay. So if you're asked to count up the number of sigma and pi bonds, you just look at the molecule and say, all right, how many bonds are there? That's how many sigmas you got. Then you look for doubles and triples. If you got a double, there's 1 pi. If you got a triple, there's 2 pi. Just add them up. All right. So let's see. What are the bond angles and the hybridizations for each one of these? Well, we just did ammonia. Ammonia has to be Sp3. Well, no, before we do that, I don't know if this is in your book, but it helps me if I set up a table. And for this table, we got how many groups? Right? Then the electronic geometry, and then the hybridization. Okay, so we have 2 groups, 3 groups, 4 groups, 5 groups, 6 groups. That's all the ones that we work with. 2 groups is linear. 3 groups is trigonal planar. 4 groups is tetrahedral. 5 groups is trigonal bi pyramid. And 6 is octahedral. Okay, so we can derive from this the fact that this is Sp hybridized, right? 1, 2. This is Sp2 hybridized, 1, 2, 3. This is Sp3 hybridized, 1, 2, 3, 4. This one is D Sp3, 1, 2, 3, 4, 5. And this one is D2 Sp3, 1, 2, 3, 4, 5, 6.
Yeah, that's in the book.
It's in the book? Okay. Back when I was a student, I had to memorize a bunch of stuff. I was going to say that word. I would set things up like this, either in tables or sometimes mnemonics would work better. A lot of my biology courses just straight rote memory. So I'd have mnemonics worked out for them if they weren't already done. And then the first thing I do, I come in and sit down at a test, and down in the margins or on the back side of a sheet, I'd put all that stuff down that I had crammed into my head just as fast as I could write it. Then when I started answering questions, I didn't have to go back and dig it out. It was there on the back of that sheet. Okay. And this will be a good candidate for that type of test-taking technique. Okay. NH3, ammonia. Bond angles and hybridization. Right, we know this one is Sp3. And the bond angles should be 109.5. Well, nominally We know they're a little less than that because of the lone pair. How about SO2? Well, let's see, we might have to draw that. Okay, sulfur and oxygen in the same family, so 3 times 6 is 18. 2, 4, 4 from 18 is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are used up. And we've got an extra lone pair there. Okay, so how do we make an octet? Well, we have two possibilities. We can make a double bond on this side, or we can make a double bond on the other side. Which means what? For this theory, the valence bond theory, we have to use a different tweak to explain it. Remember? Resonance.
I was gonna say responses. Similar.
Resonance between this one and the other one with a double bond. And we know these bonds are exactly the same length. So this is not an accurate representation. This one should be a shorter, stronger bond than that one, but it's not. Okay, that's why we have to do resonance. But when we start describing this using the theory, around this sulfur, we've got 1, 2, 3 groups. Right? So that means Sp2 hybridization and 120-degree bond angles. Because it's a trigonal planar. We have to name it? No, we don't. Just bond angles and hybridization. Okay, how about Krypton Difluoride? Okay, so we've got krypton, 2 fluorines, okay, 2 7s, 2 times 7 is 14, and then 14 plus 8 is 22. So 2, 4 minus 4 is 18. And we have to take those 18 electrons. That takes care of 12 of them. We got 6 to go. 1, 2, 3, 4, 5, 6. So around that krypton, we've got 1, 2, 3, 4, 5 groups, which means trigonal bipyramid. A trigonal bipyramid is DSP3. And the bond angles, actually the bond angle is only 180 degrees, right? Because these lone pairs like to go on the triangle. So you have the 2 fluorines up here, 180 degrees, that's it. Okay, got that one done. How about carbon dioxide? We've done that one already. So this carbon, yeah, they do specify the central atom puts the hybridization on the central atom. So the central atom, since this is linear, has to be Sp hybridized. And the bond angle is 180 degrees. ICl 5. So let's see, we've got, let's see, let's count up our electrons first. We got 6 halogens, so that's 42. 6 times 7 is 42. Now we can draw them in. 1, 2, 3, 4, 5 chlorines. So we've got 2, 4, 6, 8, 10. What did I say? 6 times 42 minus 10 is 32. And if we put 6 more around each chlorine, 5 times 6 is 30. So we need 2 on that iodine. So that's 1, 2, 3, 4, 5, 6 groups octahedral. So octahedral 6 means that our hybridization is D2sp3. Let's see, our bond angle, we won't have a 180-degree bond angle in there because that one lone pair is in apex. So the only bond angles that we see in this molecule are 90 degrees. Oops. Accidentally pressed the button. Okay, let's see if we got them right. 109.5 Sp3 for ammonia, okay. Sulfur dioxide, 120 Sp2, krypton difluoride, 180 DSP3, and it's nonpolar. Just saying. CO2, yes, SP and 180 and 90 degrees and D2 SP3. Okay. So that's how you do it. Okay. Good. I only got 2 more slides. Okay. Just a reminder, Lewis dot structure, then use the VSEPR to determine what the arrangement is for the electron pairs. Or the electron groups, I would say. Once you know that, how many of them there are, then you can translate that into hybridization and electronic structure for that matter. Okay, what are the limitations? Well, the biggie, we assume that all the electrons are localized to each atom. Right? And that requires that we invoke another tweak, the resonance. We had to add resonance because we can't smear the electrons over and make it agree with reality. Like if you have a double bond on one side and a single on the other, they're both equivalent. So they can't be double and single. They have to be something in between. It also has problems with molecules that show us unpaired electrons. Okay. Here's an example. Nitrogen dioxide. Now that's not the one with a charge on it. This is a neutral atom, and it does exist. If we were to use the localized electron model and the valence bond theory and all of its models together, nitrogen is 5, 2 oxygens, 2 times 6. Yeah, 2 times 6 is 12. So we have 17 electrons that we have to position. Nitrogen is in the center. So we have 2, 4, that's 13. So 2, 4, 6, 8, 10, 12. Got 1 electron. We have to put it on that nitrogen. Now we try to make an octet. Well, let's see if we go either side and pull a pair here and make a double on that side, or we can make a double on the other side. They'd be equivalent. But what does that do for us? You still got an octet for the oxygens, but you cannot get an octet for the nitrogen. Right? 2, 4, 6, 7. You can't go any higher. You can't put a double on that side and make it 9. Why? Because nitrogen is in the second period. It has no access to d orbitals. It cannot exceed the octet. So we're stuck with that. Okay. And if we use groups rather than pairs, we would say, okay, well, we think that it should be trigonal planar. All right, 1, 2, 3. I should have looked it up before I came in. What is it actually? I don't know whether it's trigonal planar or not. But the point is that this localized electron model of the valence bond theory doesn't deal effectively with free radicals. That's what that is, a free radical. And it is an extremely reactive molecule. All free radicals are like that. That's why you hear in the popular media, scavenge those free radicals before they damage your cells, which is one of the few times that the media is correct. Free radicals do damage. In our body, we have biochemical systems that are set up to take care of those free radicals because they're produced in all kinds of reactions. So we have to limit the exposure of our, especially our genetic material to free radicals. Okay. And I mentioned earlier, it probably just kind of blew past you, but this model says nothing, provides no direct information from the model itself about bond energies. It just says relative positions. We need something better. And that'll come next time. Hint, hint.
Do we find something better?
Molecular orbitals. Okay. Do you want to read ahead?
No, it's okay.